Okay, so this here is the video of my Core Maths Learning Journal number 3, also known as periodic functions. First of all, a periodic function is first of all a function, and second of all, it repeats over and over. So you could have this squiggle, and it's sort of like squiggle squiggle. So anyway, this is the graph of a periodic function, and so is this. This is too, although it's rather strange, but it still repeats, so it's still periodic. The properties of a periodic function include the amplitude, which refers to something about how big it is, the period, which is how long it takes for it to repeat, and then there's always the x-intercepts and the y-intercepts and such, yay. There's also this thing called the frequency, but we'll get back to that later. The period is however long it takes for the function to start repeating itself again. So this is the period, and so is this, and this is, and this, and this. These are all the period. The period can also sometimes be known as the wavelength because it's the length of the wave. This one doesn't have a wavelength because of the fact that it isn't a wave. Anyway, one of the most important waves within the periodic functions is sine wave. You remember sine, the ratio that's the opposite side of the hypotenuse compared to an angle. This fellow here, the s and SOHCAHTOA, that's the one! If we take a regular sine wave like this one here, then along the x-axis it is measured in degrees. The top peak of the sine wave is at 1, and the lowest peak is at -1. Obviously the middle is at 0. So with the degrees, you remember a circle? The one that in a full rotation has 360 degrees in it. Well, because of this, the length of one regular sine wave is 360 degrees. This has a lot to do with the unit circle. The unit circle is this dude here, the one with a radius of 1, where the x and y values on the circumference are actually, compared to this angle here, equal to the cosine and sine, respectively, of this little angle, or big angle. We can prove this by first of all saying what the ratio is, then saying that the hypotenuse is 1, and voila, there's your proof. This is also the same for the cosine. Well anyway, the unit circle has a lot to do with sine waves and cosine. The amplitude of a wave has got to do with how large it is. Say we have this function here, with the top being at 4 and the bottom being -2. To find the amplitude, we have to get the highest value minus the lowest value, that being 4 minus -2, making 6. But wait! Then we have to divide this number by 2, which equals 3. Then, ta-da! We have the amplitude. So if these are the extremities of a periodic function at 4 and -2, then the center will be at 1. The amplitude is basically how far away the peaks are from the center, which is 3 in this example. The frequency is how often something happens within a given time. This is generally only applied to sine waves, or what we call sinusoidal. I'm a T-Rex. Sinusoidal basically means like a sine wave. So a sinusoidal wave could look like this, or it could be taller and wider, or shorter or skinnier, or really long like this, or rather tall and skinny like this. So anyway, and for the record, cosine wave is within the subset of things that are sinusoidal. Basically, you have a sine wave like this, whee! A cosine is exactly the same as a sine wave, except moved over a bit, or phase shifted to the left, or along the x-axis. So, where was I? Oh, that's right, frequency! So, frequency is how often something happens within a given time. Usually, this is how many times in a second. This measurement is called hertz. Sound waves are measured in hertz, and like sound waves, light waves are also periodic. As the frequency gets lower and higher, the period gets longer and shorter respectively. Anyway, going back to the fact that a sine wave has 360 degrees within one period. Well, if you have the unit circle again, and you have a graph of the degrees compared to the sine of the degrees, we also remember that the sine of theta equals y. Looking at the 0 degrees, we can tell that this equals 0. This is right here on the graph. We then go to 45 degrees, and this is about 0.7 for sine of theta, right here on the graph. 90 degrees is also obviously 1. 135 degrees is exactly the same as 45 degrees because it has the same y value, so it's 0.7. This goes so on and so forth. Looking at the graph that we have here, we can say that this is a sine wave. Here's an animation for it. That took far too long to draw. But anyway, it's a sine wave. Also, rotation can be measured in two ways. Degrees, of which there are 360 in a full rotation, or radians, of which there are 2 pi in a full rotation. Here's a quick explanation of radians. You remember how in a circle there's a radius and a circumference, and then the radius goes into the circumference 2 pi times? Pi being 3.14152284667950284171733999995 from memory. Well, to get a radian, you first need the radius, put this on the circumference, and then get the angle made by the ends of this to the center of the circle, and voila, you have a radian. To convert from degrees to radians and vice versa goes a little bit like this. So first of all, we say that in a circle there's 360 degrees as well as 2 pi radians. If we get, say, x amount of degrees and divide this by 360, and then we have y amount of radians, which is the same size as x degrees, and divide this by 2 pi, we'll get the same answer. So degrees over 360 equals radians over 2 pi. Now, if you want degrees and you have radians, do this. From here, we can say that degrees is 360 times by radians over 2 pi, which can be simplified to 180 radians over pi. So step 1, get radians. Step 2, multiply by 180. Step 3, divide by pi. Degrees get! Yay! Now, if you have degrees and you want radians, you times both sides by 2 pi, getting 2 pi times degrees over 360 equals radians, which can be simplified to radians equals pi degrees over 180. So step 1, get degrees. Step 2, times pi. Step 3, divide by 180. All your radians are belong to us. Mwahaha. Anyway, worked examples. I think I like this font actually. Say you have an angle that's 37 degrees and you want it in radians. So you do 37 multiplied by pi, divide by 180, and you get 0.646 radians. Or say you have an angle that's 2 pi over 3 radians and you want to get it in degrees. So you get this angle multiplied by 180, divide by pi, the pi's cancel out, and the answer is 120 degrees. Whoop-de-doo-boo-doo. So we've talked about sine and cos, but what about tan? Well, the tangent ratio, that being the opposite opposite side of the adjacent is periodic but not sinusoidal. Actually, it looks sort of like this. This can be figured out by getting the y value from extending the hypotenuse of the angle so that its x value is at 1. Once it gets close to 90, it starts to get really big, as can be seen here. And at 90, it's actually infinity. It then keeps going like this and so on and so forth. So in a tan graph from here to here is a period, so this is at 360 degrees or 2 pi radians. Up there and down there go to infinity and negative infinity respectively. Now for some actual maths! Going back to sinusoidal waves, there is such a thing as a general form. This means that there is a structure in which every single sinusoidal wave can be written. For sinusoidal waves, this is y equals a plus b sine c bracket x take d. Bracket. Now to explain this being what it is that each variable does to change the sine wave. To do so, I actually start at the end. This is because the very basic form is just sine of x, but then you first of all take d from x, then times by c, and then times the sine number by b, and then add a. So to start off, here's a sine wave, or a plot of sine x. To explain what taking d away from x does, I'll need pi here. And yes, I'm using radians because radians are cool. Yes, they are! So what d does to pi, here he says, no, you're not pi. This makes pi sad, because pi is the subset of awesome. So just say that d is 1. So instead of being pi, he is now 2.141, etc., which is here, which has this value, so now he has this value. If you do that to every number, it will look like this. Weeples. So when d is equal to 1, that being 1 radian, the whole graph moves to the right by 1 radian. This is going to be called phase shifting. So we can say that the d value is how far it shifts to the right. If it was, say, negative pi, then it would shift by pi and mount in the opposite direction, which is this much, so it would look like this. If it was 2 pi, then it would shift 2 pi in the right, which would look like this. Yes, nothing happened, because it moved 1 period to the right. This also works with negative, I guess. Now for the c value. The c value fits in like this, although you could think of it like this, in brackets. To show what it does, I'll get our friend pi again. Now, say for example c was 1. This would then be saying to pi here, pi you are now 1 times pi, which of course is pi, so nothing changes. Now say for example that c was 2. It would now be saying pi you are now 2 pi. Pi is over here, and 2 pi is over here. They have exactly the same value, so that does completely demonstrate the power of c, the variable, not the programming language. So I have to ask for our friend 3/4 pi. We don't really need pi anymore. So now the c value says to 3/4 pi, 3 pi over 4, you are now 3 pi over 2, or 3/2 pi. This is a pretty good deal for 3/4 pi here. 3/2 pi, by the way, is the same as 1.5 pi. The value for this is -1, which now gets transferred to 3/4 pi. Doing this to all of the points, and some more, it looks like this. The period is now this long, also known as pi. So what c does, since the regular period of a sine wave is 2 pi, then 2 pi over c is the general period. So if we say, have our sine wave, and then we make the c value 2.5, then that would make the period 2 pi over 0.5, which is 4 pi, which looks like this. If it was 7, you do stuff like this, then boom! But much better. Also, don't forget that the maximum value is 1, the minimum value is -1, and that it keeps going off in this direction too, because I keep forgetting to draw that. So what about negatives? For this, we'll get our friend half pi to appear. Now, if c was -1, it would be saying, half pi, you are now negative half pi. Now this is this point over here, which is y value of -1, which means that half pi's new value is over here. Doing this to everything looks like this. So a negative value turns the graph back to front. So here's another example of the c value. Yay! So let's just say c is equal to -pi. Since the regular sine period is 2 pi, and new one is 2 pi over -pi, which is -2. So if this is regular sine wave, if this is one with a period of 2, wow, that's bad. Then this is one with a period of -2. For the record, 2 pi equals 6.28318, etc. So now for the b value. So with a sine wave, the c and d refers to the x value, so that when it gets signed, it's different. The b value is multiplying after it gets signed, and so it changes the y value that we already have. For this, we'll get our friend to appear. The b value now says you have already been signed. Now multiply your new y value by 2. Since it's currently -1, it will go twice as far down from the center and become -2, which when done to the whole line looks like this. So changing b changes the amplitude. So if the amplitude is regularly 1, then b being 2 would make it 2. B being a half would make it a half, and so on and so forth. Although writing it like that doesn't make much sense when it's split up like this. So b equals the amplitude. Yay! Now for the a value, which is really easy. So all of this has been doing stuff changing x and the sign of it to give you a value of y. Well, that's a function. So adding a, or putting a plus in front, it does the same thing. Well, guess what? It just adds to the y value. So if you have a point, adding a will move it up by a amount. Well, if a is negative, then it moves down. So you have your sine wave, and a can equal 2. Getting our friend pi out here, whose value is 0, a is saying to it, your value is now 2 more! Also known as 2. So instead of 0, he is now up at 2. Doing this with the whole sine wave of, say, a being 3, would look like this. Or a being -1/2, it would look like this. A being 0, it would look the same. Simple. So the a value is the y shift or the vertical shift or something along those lines. So now let's combine them all. So first give all these variables a value like this and a graph. Looking at this, we know that it'll be moved up over here. We know that the period will be 4. This we know will be moved up 2, and we'll have an amplitude of a half. Putting these together will look like this. Here's another. This will be interesting. So it'll be phase shifted pi to the left. The period will be -4 pi, which will make it back to front. The amplitude is -3, so it will be 3 times as big. And the negative, so upside down. So combining back to front with upside down looks normal actually, but it used to be this big. And a being -1 will shift it down 1. All these together looks like this. As you can see, the period is 4 pi, it's being shifted down 1 and pi to the left, and it's being back to front and upside down, so it looks the same as a regular sine wave, and the amplitude is 3. Ta-da! Also, all these variables do exactly the same thing to a general form as a cosine wave, except everything is shifted to the left by half a pi. Also, it's the same for tangent. Almost. Here's sine and tangent. A still moves up, D still moves sideways, C still squishes and stretches it. B does change the amplitude, but it's harder to notice, as it doesn't equal it. If B was 2, it looks sort of like this. Now this is being stretched upwards, and it has the same x-intercepts and all, but the amplitude is still infinity. If it was 0.5, it would look like this. It is squished, but difficult to tell. So the last part is solving stuff. If you're given a function for y of x, and then you're given what y is, you need to find x. Here we go. This is the method my maths teacher told me. If you're given something like this, you're also given a range for where the answers have to be between, like this. So to start off, we need to get rid of the cosine by doing arc cos. I'm using arc cos because I think it looks nicer than cos to negative 1 or inverse cos, and it's also easier to say, and because it doesn't conflict with the semantics between multiplicative inverse and compositional inverse, because I know what that means. So anyway, do this and you end up with 3x equals pi over 3, or 60 degrees. But I'll stick with radians because they're cool. They are cool! So now we have one answer. But if we remember our cosine wave, if something is x amount for the start of it, then you can get the same answer from x amount away from the end, or 2 pi take x. So now we have pi over 3, and 2 pi take pi over 3. Also known as 6 pi over 3, take pi over 3, or 5 pi over 3. Now we need numbers between 0 and 2 pi, and looking over here, it seems we'll divide everything by 3 later on to get our answer. Because of this, we need to look at 3 rotations instead of 1, because dividing by 3 will make it fit between 0 and 2 pi. So if we have answers here and here, then we can also have answers here and over here, as they all have the same y value, which is what we want. So we can add 2 pi to these answers twice! Then we get more answers. So, now adding 2 pi to these, or 6 pi over 3. So now 3x equals all of these. Now to get our answers, we need to divide by 3 because x is multiplied by 3 here, so that gives us these. If you notice, the smallest one we have is larger than 0, and the largest one is smaller than 2 pi, or 18 pi over 9. There we go! We could also convert to degrees, which is still between 0 and 360. Another example. Yay! So we have 2 sine a half x equals 1. This means that sine a half x equals 0.5. Oh, and let's have different restrictions this time. X has to be from pi to 3 pi. So then we arcsine both sides, or sine of negative 1, or inverse sine, or whatever. So then we get half x equals weight. So this equals pi over 6. Looking at a sine wave, pi over 6 is obviously in the first quarter of the sine wave, so if you have something that's far from the start, in this case pi over 6, then its counterpart will be pi over 6 in the other direction from here, being pi take pi over 6, because here is pi. So going back to the work, and we're looking at there's a half in front of our x, which means we're going to have to multiply everything by 2 later on. So since we need answers between pi and 3 pi, all we need, which we multiply by 2, will fit in here. Obviously pi over 2 and 3 pi over 2. See here. Here's a double sine wave when it gets multiplied by 2, to get our final answers, which we want between pi and 3 pi. When this is, as a regular sine wave is, these are now between half pi and 3 halves pi. So half x needs to be from half pi to 3 halves pi. Arcsine 0.5 is pi over 6, but this doesn't fit the constraint. Pi take pi over 6, that being 6 pi over 6 take pi over 6, or 5 pi over 6, does fit the constraints. The next one with the same answer will be another 2 pi along at 2 pi plus pi over 6, which is outside of the range. So that leaves us with only this answer, which is finally 5 pi over 3. So we have found out all the answers between pi and 3 pi within this function. Try it on a calculator, or Google's built-in one. 2 sine over half times pi over 3 will equal 1. And another example! First I'll do the boring stuff, and I've made these common denominators. Now here has a minus 3 pi over 12, or a quarter pi. This means that later on we'll add a quarter pi. Because of this, any value over 2 pi take 3 pi over 12 is invalid, because it will end up being bumped to over 2 pi, which is bad. Also, anything up from negative a quarter pi has a chance of being right, as it will be bumped past 0, which is good. Now, 2 pi over 12 is in the first quarter, which means that it has a counterpart at negative 2 pi over 12, as well as 2 pi take 2 pi over 12, or 22 pi over 12. If you notice, 22 pi over 12 is larger than 2 pi take 3 pi over 12, or 21 pi over 12. So this is out of the question. This leaves us with 2 answers, which equal this. So that's about it for solving things. Now for applications in the real world. Periodic functions happen in many things in the real world. For instance, tires, which rise and fall because of the pull of the moon's gravity as well as the sun's a bit. This happens twice a day, which may look something like this, with the x value being time of the day and y value being how high the water is. The period for this is 12 hours, the amplitude is about 2 meters, and the frequency is twice per day. Sound waves are also periodic and measured in hertz, so if some guy says blah, then the vibrations it makes look sort of like this, or perhaps like this. So most likely not sinusoidal, but still periodic. Human hearing ranges from a low of 20 hertz to a high of about 20,000 hertz. But yeah, sine waves are periodic. Also light waves, which obviously means every other type of electromagnetic waves, are periodic. Visible light has a frequency from 405 to 790 trillion hertz, or terahertz. Biorhythms, which is a pseudoscientific theory that various aspects of someone's life, like their intellect, their emotional state, their physical attributes, etc., can be predicted as periodic mathematical functions into the future, are also periodic. Sunspots. These are spots on the sun that happen because of weird magnetic stuff that I don't know of. The amount of sunspots seems to be pretty periodic, on an 11-year period or so. Also, undampened springs, playground swings, and something else are periodic. That's basically it for the CML sad phase. So, TLDR, also known as a summary. Periodic functions. Functions repeat over and over like this. There's a period, there's the amplitude, there's a maximum, there's a minimum, or highest and lowest points. Sine, cosine, and tangent waves, when graph look like this, this, and this. For sine waves, amplitude is 1, maximum is 1, minimum is negative 1, period is 360 degrees. Tangents have an amplitude of infinity. These can be made with a unicircle looking at this angle and the sine and cosine of the y and x values respectively, this dot going around the circle as it gets bigger. The angle, that is. Tangent is plotting the y value of this dot, which always has an x of 1. Inner rotation is 360 degrees, or 2 pi radians. A radian is this. This is how you convert between degrees in radians. A sinusoidal wave is like a sine wave, but any period, amplitude, phase, and y shift. The general form of a sine wave is a plus b sine cx take d, where a is the y shift, b is the amplitude, 2 pi or 360 degrees over c is the period, and d is the x phase shift. This is the same for the general form of cosinusoidal and tangential waves, except b doesn't equal the amplitude of the tan wave because it's also infinity. Frequency is how often something happens, often in seconds, so it's things per second called hertz. To solve a function for a given sine wave in a given range requires algebra, trigonometry, and knowing that all of these values have the same value. This also works for cosine and probably tangent. Periodic functions happen in real life, so there. And that's about it. Metacognition. Has this been a successful way of completing my CML? Yes, I believe so, as I find the drawing and video editing elements to be enjoyable and give me motivation to do work. Have I learnt more about periodic functions from doing the CML? Yes, I believe I have, and I've also gotten a better grasp on how to solve them as well. How can I improve my CML for the next time? The biggest element is probably starting it early so that I don't get stressed close to the due date, which happens. Bum.